Hi everyone, welcome to the course series of quantum channels for quantum networks. Hopefully in these 3 hours, you will learn something new about quantum channels and how these series tools can be used for modeling quantum networks. And I'm Quntao Zhuang. I'm assistant professor at the University of Southern California. And this course will be co-instructed by Anthony Brady, my postdoc. Great. And here's a short table of contents. We'll begin with some introduction, and we'll go with some general description of what quantum channel is. And then we will finalize to Gaussian bosonic channels, which are the typical models we are going to rely on. And then this model will be also applicable to single photon cases, which will lead to like more special channels. And eventually we'll have some recap and exit survey. So first, to motivate why we care about quantum networks and the quantum channels, well, I believe the previous courses probably give already some motivations, but let me recap a little bit of. So in this era of quantum engineering, there are many quantum information engineering applications, like quantum sensing, where non-classical sources like squeeze light and entangled light can be used for measuring different parameters. For example, in the famous LIGO experiment. And in quantum computing, there were many algorithms already there developed, and also different ways of realizing these calculations in different platforms, like adiabatic algorithms, circuit model, or measurement-based computing. And there's also NISQ quantum computing proposals where people are building and demonstrating quantum advantages. But there's also quantum communication where people try to either share secret key or actually try to use entanglement to assist the communication rate, like entangled assisted communication. And these 3 areas are not isolated. They are closely connected. For example, quantum sensing can be used as a subroutine in communication. So when you send things and the receiver side, essentially the receiver is dealing with a sensing problem to measure and extract information from the received quantum states. In quantum computing, as it is universal, it will enable receiver designs in both communication and sensing, and communication then would be able to enable entangled sharing between long distance to enable distributed computing and sensing. And so from this, we see that there's a global, or there's a central item here, which is a quantum network that will enable the power of all these different applications. In the future, let's imagine the future, if we actually build this quantum network in a global scale, then we'll connect a lot of things to this quantum network, like quantum computers, which can solve hard problems, and these classical transceivers, which will be able to extract secret keys. Also, these quantum sensors will be able to connect with each other by entangling them, and then provide ultra precise performance in different estimation problems. And also there's many different physical platforms involved. Each platform have its own property and its own pro and cons. So in this case, in this quantum networking case, we are mostly focused on a few of them. For example, transduction systems that go between optics and microwave cavities, which are good for computing. And bulk optics and nanophotonics are the most important one for networking, because only light can travel at the light speed and reach different places in the on Earth quickly. So this is Paul 1, but it's a simple task. So Anthony, do you want to take over this part?
Yeah, let me. So yeah, this is sort of like a warm-up poll. There'll be a few of these throughout the lecture, so this is just the first one. And so let me open up this poll now. Relaunch poll. Okay, that should be appearing on your screen. So okay, this is just a simple poll. So what are photons good for? They're good for quantum sensing, quantum computing, quantum communication, or all of the above. And like I said, this is a little warm-up poll. They'll be a little more detailed later. But for now, you can answer this, and when it's a majority, I'll end the poll and go over the result. So I'll wait for about one more minute. There's about 77% of people who answered so far.
Meanwhile, during the lecture, if you have any questions, feel free to put in the Q&A part, and we will try to answer live, either by typing or just answering by speaking it.
Yeah, maybe I'll just say this also, because there's a timer. These poll questions, I'll wait for about 1.5 minutes to 2 minutes, and then give the answer. So it's about 1.5 minutes right now. So I'm gonna, since this is a simple one, I'm gonna go ahead and close it. 82% of people have already voted. So let's end the poll and share the results. Yeah, so yeah, all the above, right? You can actually go to the next slide, Quntao, where it says this.
Yeah, so probably I didn't make it completely through, but let me emphasize a little bit. Yeah, it's photons are useful not only for communication. It is the most necessary thing in communication, but in computing and sensing, it also provides another angle or approach for measuring things. For example, in computing, then there are different approaches, and photonic-based ones are one of it. So it could also be useful for computing.
Yeah.
So let's continue.
Yeah, just by the way, yeah, so typically, let me just say this real quick. Typically, like I'll be like a poll, and then it'll be like an answer, a more detailed answer right after the polls are up. So the more like the more sophisticated questions will have an answer right after. Okay.
Great. So let's dive into quantum channels and general descriptions, and we'll get a bit technical. So let's begin with a very high-level introduction of quantum mechanics. So in here, we will describe quantum operation, quantum channels, and a lot of complicated notions. But the actual starting point of quantum physics is pretty simple, in the sense that we believe our universe is evolving under a unitary dynamics. What does that mean? Well, you might ask, well, there's of course noise process. If I do experiment like a thermonization process, then certainly the system is not evolving under a unitary dynamics. So what happens in that case? Well, in that case, you're not including the environment that actually thermalizes the system. So if you include the thermal environment, the environment and plus anything else that is interacting with the environment, then eventually you can think about the whole system as a unitary dynamics. And another thing is that we believe that the whole universe eventually is a pure state, meaning that if you include everything relevant to your system, eventually it's going to be a pure state, or in some sense, it could be described by a pure state. Well, a thermal state at finite temperature, of course, it's not a pure state, but you can include the environment into the system. Then overall, it's going to be described by a pure state. So these are the general principles. Well, I will comment that a measurement is probably the only caveat. When we describe measurements, there were different ways of interpreting it. But let's say if you don't know the measurement result, then still the volume picture of measurement can still be described by unitary process. So in more detail, mixed states come from this partial trace process, or in other physical words, by looking at a smaller system in a big system. So let's take the universe S plus E in a pure state, psi SE here. And what do we mean by partial trace? Well, we mean that we are not looking at the whole system S plus E, this pure state, but we are looking at the partial system S only. And then we want to describe what is the state of this system. And in this case, it will be described by a density matrix. And this trace process, if in the matrix representation, it can be done by just summing over all the bases in the E system. So let's take a general example. Let's say S and E is in pure state psi, and in general, we can do this so-called Schmidt decomposition of a pure state, meaning we can always find orthogonal basis in S and orthogonal basis in E, such that this general pure state can be written as a superposition of all these product of pure states. And these lambda i's are going to be the spectrum of the system. And in this case, if you take a trace, as I said, you can sum over E in any basis. And in this particular case, we can sum over this same basis that we do for this Schmidt decomposition. So if you do this algebra, this is the bra and this is the cat. So we write this whole pure state density matrix out, and then we sum over the J. The J's are the E, the basis for E. So then this J get interacted with this I2. Let me annotate a little bit. So J, these two gives you a delta function, and this J and another E also gives you a delta function. So eventually you sum over and get a reduced density matrix as a fully diagonal state in this J basis. And it turns out that this spectrum in the Schmidt decomposition are automatically the eigenvalues of the reduced density matrix. And you can do the same for environment E. And if you trace over the system rho S, you will find the same set of eigenvalues of rho E. So that's just a additional thing coming from the fact that the state is pure. Let me clear. And next slide. Yeah. So now that we know how we do looking at a smaller system from knowing the bigger system, we can also reverse the process. So let's say we start from the final mixed state we arrive at. So this diagonal state in this eigenbasis J of the system S. And we can just append the environment. This is so-called a purification process. Essentially, you have a system, you try to introduce environment E such that you can write out a joint state SE so that the reduced state of this is the initial state you have. So you can do it in different ways, but this is one way to do it. First, you diagonalize the reduced mixed state, and then you append this environment basis E. And from here, we just see that the dimension of the environment only has to be the same as the dimension of the system. So to guarantee there's a purification. So we just write out this pure state in this form. From these eigenvalues, you get the spectrum. And this is exactly that Schmidt decomposition. And here we see that universe S plus E is a pure state. And the unity degree of freedom you have, meaning that I can have different type of environment to purify the same system, right? So because here it's a description, so you are allowed to introduce different ways of purifying the system. So if you do another unitary on the environment, it wouldn't change the reduced state. So it's another valid purification. So the reduced density matrix and the purification are two major tools we will use to describe to enable the description of quantum channels and quantum operations. And let's begin with this picture where, okay, there's a Q&A, loss in the derivation, what is purpose and what does this derivation conclude? So this derivation enables you to analyze, let's say, the relationship between looking at the whole system and looking at the subsystem. And in practice, when we actually tackle quantum channels, we will usually look at the whole system and look at the unitary dynamics. And then this tracing process will lead to the so-called cross operators of quantum channels. This will become clear as we proceed. So bear with me a little bit. So right now we just go through two of the basic maths that we'll use. One is purification and one is reduced density matrix. So now let's look at unitary dynamics again, which is the only thing you need to know to understand everything about the quantum process. So here we go. So you begin with a system, and as long as you find the proper environment, you can derive some unitary process, USE, between this system at E, such that the final state is evolved through this unitary dynamics. So we do a tensor product of the system state and the environment state, and it's a unitary evolution. So that's what we look at the whole system. But if we only look at the subsystem S, then it turns out that this will give rise to a quantum channel. And in mathematical language, this is so-called a completely positive trace preserving, which is a CPTP map. And as we see, so we know the general state of the global system here is the described by this USE acts on the initial state rho s and the environment state sigma e. So the only thing you need to do to look at the subsystem is to trace out the environment E. And observe that all the operation involved in this input-output relation. So here it's a general input-output relation. This is the input state rho s, and this is output state rho s prime. And all operations here involved are linear. These unitary operations are linear. Linearity in general means that I apply a unitary to superposition of two states. It will create a superposition, but the unitary acts on the two states. Okay, let me write another state psi here. So it will act on it linearly. And it's a map between the input state to the output state here. Okay, there's another question. It's supposed to be comprehensible. I'm somewhat familiar with linear algebra, but now the symbols, variables have defined. Okay, so we have assumed some initial knowledge about quantum mechanics in this course because it is a level 3 or above, like a graduate level course. But okay, so to make sure everybody can understand, let me maybe briefly go through all these notations that we are using, which is the Dirac notation. I think that would be, yeah, that would be helpful. Okay, let me see. I need to find a large enough blank space to do it. Okay, here we go. We have this blank space. So you might from coming from linear algebra, you might learn quantum mechanics from density matrix. So you might learn it from a matrix point of view. So a state phi is in general a vector, and let's say you can find a basis state. So let's say this builds up your Hilbert space, phi 1, phi 2, up to phi n. And these are also normal in the sense that they're inner product. So this is the notation for inner product. And these are the state vectors, which we write in a cat. And its complex conjugate, C, we write it in a bra, which is the inverted fashion. So inner product, this is inner product, which is the, when we put a bra and a cat together, they automatically mean inner product. So in other representation, you might have learned inner product from, let's say, if you come from, let's say, condensed matter or energy well potential calculations, if you learned about this in the past, then inner product, you can do it in a, let's say, in the position basis or in the momentum basis. So it's going to be a integration. So this is inner product. In bracket notation, we just need to put this bracket and cat together. And there's a formal way you can actually go between this bracket notation in the sense that I can insert any identity operation, and any identity operation can be written in a state basis. And let's say this is integrating over X. And now you automatically arrive in this position basis representation of an inner product. Okay, coming back to states. So now you have basis states, and they are orthogonal, meaning their inner product are 0. the any state phi can be expanded in this basis phi I. And it's a linear superposition. So any pure state can be written down in this way once you find this basis state. So if we want to write down the density matrix in this bracket notation, we just put this bra and cats side by side like that. What this means is that you have this cat part and you need to append the bra part. So it's a Cj star phi j. And in general, this will look like a density matrix to you once we write it in this form. Okay, is I here. And now you see this is essentially a number and its basis. So what you can do is, let me clear out some of this part so that I have more space. What you can do now is, okay, I can write down a matrix where this phi 1 up to phi n is the basis. And now I can put in all these numbers, okay, C1 star, etc. So Ci, Cj star. So now you have a density matrix that describes this state phi. And if you are familiar with matrix representation, then and linear algebra, then you can play with these explicit forms of matrices. But because we are describing a general theory, we are more inclined to utilizing this simplified notation. So that you don't need to explicitly write down a big matrix every time you try to write down things. And what we did in the past, the trace and the purification, you can essentially understood then through these density matrices as well. So if you do trace, then meaning that you are actually summing over certain elements of this density matrix, summing over them to actually condense them into a reduced density matrix part. So I don't think we have the full time to go through all of these derivations, but this is the language we are going to use. I hope that will at least help a little bit so that you will learn something from the course. Okay, so let's continue. So now we're at this here where we start from the unitary evolution of the system and environment, and we're looking at the partial trace over the environment to get the system. So now we arrive at a quantum channel. So all you need to do is to recognize that this is a linear map and it maps quantum states to quantum states. So this is the formal definition of a quantum channel, which is here. We use this notation n or phi or psi sometimes. So essentially you can write this as a function with an input that is density matrix or density operator, and you get another density operator equal S prime. So this is the simple way of denoting a quantum channel. And to further simplify, so here we are considering a general quantum state of the environment, sigma E. So it could be pure, it could be mixed. But as we said, if you include enough things, eventually everything is pure. So here for simplicity, we can just denote this initial environment state in a pure state, E0. E0 is an arbitrary notation we pick for whatever pure state you begin with. So whenever this is not pure, we can of course just include more environment and purify it. In other words, in the previous picture, let's go to the, oops. Okay, I will stick with this picture. So it's essentially, if you have a S system and E system, and you have a unitary USE, and now you find E system to be a non-pure state, what you do, you can include another E prime system to purify this, such that E and E prime is a pure state overall. So now you can introduce another identity operation, which means that nothing happened on the actual purification. So then the overall unitary becomes the original unitary tensor's identity. And for simplicity, we don't write out identity explicitly. So eventually you can deal with a pure state of the environment. So that's the essentially this what we mean by you can always choose a pure state for the environment. So now we have chosen this pure state of this environment. Now we can pick a basis to do the trace over the environment. So let's say this environment is in E0 with one of the bases. You can pick the complete basis by just doing a orthogonalization process of whatever state you're interested in. And therefore, you can do the trace in this basis EK. And now what you need to realize here is that this rho S and this environment state is a tensor product. So therefore, you can essentially think about these unitaries that act on both the system and the environment, while this E state is for the environment. So you can manipulate this form a little bit such that the rho S comes out at the last, while the actions on the environment can be condensed together. So what this means is that this is a unitary operation. Unitary means that it's a matrix that satisfies U dagger U equals I, if you know linear algebra. And now you can actually act this state, this E0 on the right-hand side, and also do an inner product with another state EK. So this overall thing is what we call as a cross operator. And it's nothing just comes from, it's nothing but a simple object coming from unitary dynamics and basis for the environment. And now we have arrived at the next slide, which is this so cross representation of quantum channels. And in general, if you tell me, if you ask to specify a quantum channel, the most general way is to specify the cross operators, but it might not be the most simple way. There were other ways of specifying it, but this is the general theoretical tool you can use. So just to review this overall, we have a system density operator, environment density operator. We have a unitary interaction, and we traced over the environmental basis EK. And we have all these cross operator LK defined now. So what we are going to do is to specify the unitary and then arrive at the channel, and then we will calculate things and analyze things to actually enable analysis related to quantum networks.
One sec, could you go back one more slide?
One more slide.
If you could go back, it's a little hard to distinguish rho from E.
Rho from the, oh, okay. So yeah, so let me clarify. This is E, and E0 is here, EK. So all these things related to environment is E, meaning this is a basis for the environment. E0, E1, E, M, let's say. This is a basis for EK, and rho S. So the only rho appears here is rho S, which is the system state. Okay. Great. What's special about E0? Well,
Nothing.
Just nothing special about E0. You can pick any pure state to actually do this. Well, if you pick a different E0, depending on what state you pick, you might end up in a different channel. That's what we say. But in a general description, you can pick different states. Later, we will see some examples. Okay, you see that here E0 will describe this density, how the density operator evolved, because these cross operators are going to dependent on E0 here. And one property you will immediately see is that this is complete. It has to be complete because it's coming from unitary and describing pure state evolution. So everything is normalized. So of course this should be complete. And this also can be mathematically verified. You sum it over K, and this is a basis in the environment. It's a complete basis. So you sum over everything, you get identity, and you get nothing but the inner product of the environment. Okay, so let's do some examples, erasure and depolarizing. Consider a two-level quantum system described by the quantum state phi and the erasure state, which lies outside of this Hilbert space, meaning that this two-qubit state, you have basis 0 and 1. And this erasure state is an orthogonal basis, orthogonal to both 0 and 1. This is essentially modeling the fact that sometimes a quantum process, a quantum machine operates, but sometimes it raises a red flag saying the system is in error. So maybe something malfunctioned, but there's an indication, a red light flashing, or some indication of it, which makes you realize that it's essentially entirely orthogonal state to what this system should be at. So essentially, this is modeling this erasure or this error process. So so this is the input-output relation of this state, essentially here, psi, and you have error probability. So there's a epsilon probability of having the erasure happening, and there's 1 minus epsilon probability of outputting the original state with no error. And so given a qubit, for example, you can also have a depolarizing channel, which means that with property P, I'm going to replace the input with a fully mixed state, and with property 1 minus P, I'm going to produce the original state. So we can, okay, maybe let's go through this. So let me maybe just write out the unitary representation of the first one in a few minutes. So as we said, everything is a unitary, right? So here there's an input-output relation. It looks like not a unitary process because it's a probability mixture of two things happening. So what you can do is you can think about what really goes on here. You have a let's say you have a big system S, which might be in an arbitrary state psi, and you have an environment, and the environment can be in a erasure state in the beginning. And now I can say, so what should be the unitary that actually represent what's happening here? Well, this just looks like a swap of the two sides, right? If you swap the system and the environment, then you will see that the system becomes the error state and the environment will be the whatever state you input. So here, this could be just a simple swap operation. And once you swap it, then you are guaranteed to produce the error state and the system in error state and environment in whatever input state. But this is not whole story, because here you made sure that the input state rho s just becomes the erasure state. So a swap is not enough. What you need to do is to enable a probability mixture of having a swap and not having a swap. And that's going to be realized by introducing yet another environment. So I can introduce another environment, which is in a superposition of two states. Let's call it, let's be consistent. So epsilon is the error probability of being erasure. So let's do this state. So this is going to be a control qubit acting on the unitary here. And unitary now is just a simple swap. So this is showing you how we can come from a quantum channel and go to a unitary representation of it. You have a environment E in an erasure state. You have another environment in a superposition of 0 and 1. And this environment will control meaning that if it's 0, you do this, you do identity, you do nothing, which is guaranteeing that, okay, I believe I have a,
yeah, I think
1 minus epsilon switched. So this is 1 minus epsilon doing nothing. And if it's, if it's 1, I do this swap operation, which guarantees that the system is in this error state. So this in general represent a process where you start from any quantum channel, you can end up with a unitary. There's a question. It seems like the channel has a state added to outer product of state, which is like a vector plus a matrix operator. So we can't do this mathematically. Could you solve my question? Well,
I just I just answered it.
Oh,
I
you
think
just answered. Okay.
size, yeah, big size, but that's supposed to be just a general state. So that's a density matrix. And then the outer product of epsilon epsilon, that's just another density matrix.
Mhm. Okay.
Just a probabilistic combination of density matrices.
Yeah, so it's a probability mixture of two density matrix. It's still another density matrix from that point of view. All right, let me clear this drawing. And for depolarizing channel, you can also work out the purification. It's a bit more involved, so we're not going to cover it, but you can think about it. All right, and so let's say you can always find the unitary extension, but sometimes finding the whole unitary extension is too much to ask for, meaning sometimes it's not necessary. Sometimes you are just satisfied with so-called isometric extension. And what this means is that you're not writing out the whole entire unitary, but what you're doing is you're writing out so-called isometry, which is essentially a lazy version of a unitary extension. Coming from this cross operator LK, you can actually just append the upstream basis EK, and you can sum over K, and you can verify that this is forming isometry from the system S to the joint state S and E. And isometry is in the sense of these two relations. So if you go from S to SE and then to this dagger, you go back to S, you can recover this identity operator, meaning if you do this and its inverse, nothing happens on the system. And if you interchange the positions or the order of these two operations, then it will be an identity operation on the joint system S and E. So sometimes you might see people just writing out isometry instead of unitary, because unitary requires more work in deriving out all the things, but isometry sometimes saves some trouble. Okay, so now before we jump into the business of Gaussian channel, let's just in one slide give an example of why we do this trouble of purifying everything to unitary extensions. What's that going to buy us, right? So it's going to be a very useful tool for quantum information processing analysis. Anytime you calculate entropy, you calculate quantum channel, you calculate the quantum channel capacities, these purifications and unitary extensions appear all the time. And let's give a simple example. So let's consider this quantum capacity calculation, and in the single letter way. If you know what this means, that's fine. If you don't know, that's fine, because here all we are giving is just expression. So let's say this quantum capacity is a maximization over the input state rho s of the entropic quantities. And here, this is the Von-Neumann entropy of the output, and this is the Von-Neumann entropy. So this is the output. This is the environment. And all you need to do is calculate the entropy difference to get this so-called coherent information. This is so-called coherent information. And then you maximize over the input state, you get a quantum capacity of a single shot. So here is what's this unitary extension purification is going to be useful. So you have a general quantum channel NS, but what you can do is you can incorporate the environment E here. And now this S system and E system, you can guarantee that there's unitary that is evolving this S plus E system, and now becomes E prime S prime. So a general input state rho S might be mixed, and we don't want to deal with mixed state because it might be it might be cumbersome to actually write out, and we like pure states much better. So what do? You purify the input state. General state rho S here, you can always do this diagonalization in basis and then extend to purify this in a joint system A plus S. So this is the second slide we see. You can extend a mixed state rho S to a pure state between some ancilla A. So now we have A, S, and E initially in a pure state, which is what we like, and which is coming from the belief that if you include everything, it's always a pure state. And now the dynamics, if you include everything, it should be a pure state. It should be a unitary. So here we have a unitary U, and then the environment A has nothing going on, so it's identity. So it's U tensor identity acting on this joint system. And we can write out the output state as A prime, S prime, E prime. Okay, so now that you understand this picture, you're going to buy yourself a lot of things. Well, to begin with is that you automatically have the so-called complemental channel. So this NC is so-called a complemental channel. So a channel is describing how S is mapping to S prime, right? But if you look at on the other side, environment and the system here is entirely symmetric, right? So they are just going through a unitary dynamics, and then you're looking at one of it. But how about you can look at the environment as the output? So now this is your original channel, and this is another quantum channel because it's also coming from the unitary, it's a linear, and maps quantum state to quantum state. So this is another quantum channel called the complemental channel or complementary channel sometimes. And so these are the two states output, and note that here the joint state is not a tensor product of these two output state because they are just looking at the subsystem. They are not looking at the joint system. The joint system you require the host unitary to analyze. Okay, so what does that buy you? So now we look at again here what's this quantum capacity of coherent information is about. This output is essentially the S prime system. Let me erase these words. Output is S prime system, and the complemental is E prime system. And therefore, you can see, let's say, this environment output entropy, by definition, is the E prime's entropy. And because the output state A prime, S prime, E prime is also pure. So if you have a pure state, then the two reduced density matrix have the same entropy that's coming from basic knowledge in quantum mechanics. If you have a pure state A and B, if the whole system is phi, is pure AB, then this means that SA equals SB, the entropy are equal. This can be derived from the Schmidt decomposition, where you can show the A and B essentially share the same spectrum and then therefore the same entropy. So by this property, then you see that E prime entropy is equal to A prime and S prime, which is essentially what's left over if you get rid of E prime. That's the pure system A prime, S prime, E prime. If you get rid of E prime, you get A prime, S prime. So that's the entropy of the input state, purified input state, which we write as psi rho S. It's a purification of the state rho S. And now the channel is acting on the system while the ancilla, the purification ancilla is identity. So this would admit another way of expressing the same quantity. And this is actually, in most cases, when you see quantum capacity, you probably see this expression appearing. So further simplification coming from this formula and then solving some quantum capacity results are not within this course coverage. But let me just say that these tools are going to be very useful in analyzing all these quantum channels. When you look at a quantum channel, you always look at the whole system, and that will simplify a lot of these proofs. Okay, let me clear the notation and let's go to the next slide. So, okay, that's poll one.
Yeah, so okay, so here's a poll. So we looked at the erasure channel before, which has this representation here. You get the state with some probability 1 minus epsilon, or you get an erasure state with some probability epsilon. So you can concatenate two erasure channels. For example, you can have one with epsilon 1 first acting on the state, and then right after that with epsilon 2. So here's a simple question. So the concatenation of two erasure channels is another erasure channel. You'll just have to take that on faith for now. With some erasure probability, epsilon 1, 2. And the question is, what is the erasure probability? Okay, and there's a hint. The erasure probability is 1 minus the transmission probability. And what I mean by this is, for example, up there for this first erasure channel, the transmission probability is 1 minus epsilon. So yeah, that's the question. Let me open up the poll. Yeah.
The pool might be blocking the question a little bit. Can you move it to the empty spot? Okay.
I can't, but other people.
Oh, okay. Yeah, everybody can move it actually.
Yeah.
So if you are blocked, you just move this poll to an empty spot and look at the PowerPoint.
Yeah. Or you can close it, look back, and then reopen it if you need to.
Okay, there's a question. Was an Excel acting on the initial pure state argument of S in the box question? Okay. The psi S notation is a purification. So while you answer this poll, I can write here. So psi rho S is a purification coming from S to A and S. So remember E, S, and A, and then unitary, and then identity. And so this N tensors I is a map coming from AS to A prime S prime.
Can you, to what extent can you, yeah, I mean, they're similar. So this question is about the analogy between quantum and classical erasure channel. Yeah, I mean, so you can have a bit that takes either value 0 or 1, and maybe you just simply lose the bit, right? So that's like you lose the bit with some probability epsilon, so the bit just gets erased. Here, now you don't have for the quantum case, you don't have a bit. Now you have a qubit. You could be in a superposition of 0 or 1 states. So these are very related.
So furthermore, so the quantum erasure channel, if you only allow to input diagonal states in 0 and 1, then it automatically becomes a classical erasure channel. So in that sense, it's the same channel.
Yeah. Okay. And okay, so let me look at these polls now. So that's about 58% of people have answered them. It's about 2 minutes, so I'm going to go ahead and close it. Let me end the polls. And then, yeah, right. That's the right answer, C. So let me stop sharing. Can you go to the next slide, and so we can explain the answer?
Sure.
Yeah. So in this case, it's an erasure channel. So either the state gets transmitted or the state gets erased. And so the transmission probability for the first channel is just 1 minus epsilon 1. Okay, that just comes from this little formula up there. And then the transmission probability for the second channel is just 1 minus epsilon 2. Okay, so then the total transmission probability is just the product of probabilities. So you have that. And then the erasure probability is just 1 minus the transmission probability. This was in the hint. So yeah, that's why the answer is C.
Okay, there's another question. Density matrices might be useful in classical computing algorithms. Well, in some sense, everything classical is quantum. I would like to say that. And so anything you write down for quantum in the diagonal basis, if you allow everything only to be diagonal, then it becomes a classical description. But whether you need the whole quantum description is, of course, not necessarily for classical. Okay. So now let's jump to Gaussian bosonic channel. We are 15 minutes, so I think we are doing okay in terms of time. And why we care about Gaussian bosonic channels, where we are thinking about quantum channels. We want to understand how light propagates. And in terms of describing light propagation in open space, in fiber, and different places, it's a bosonic channel in general, and it's also Gaussian. So that's what we need to know about describing quantum light propagation. So to describe light field, let's start with a simple toy model, quantum harmonic oscillator. So free electromagnetic field is a bosonic field and described by a harmonic oscillator like Hamiltonian. So Q squared, Q is the canonical position and P is the canonical momentum. And they have this canonical commutation relation, which in this case, we have let H bar equals 1, so that here, let me just write down, H bar equals 1. And then if you learn about the basic quantum mechanics, you'll know there's an annihilation operator, A dagger, you can introduce, which is essentially a combination of Q as a real part and then P as an imaginary part. And here, square root of 2 just come from the scaling choice. You might see other papers or other places where you don't have this square root of 2, where people choose H bar equals 2. But in this case, we're going to stick with this notation. And here, these annihilation operators have the usual commutation relation. Therefore, these annihilation operators allow you to define this number state, which is the Fock state of this EM field oscillator. So we can define this number operator, A dagger A, and you can write this harmonic oscillator in this simple form. And therefore, you can immediately see the eigenstates are Fock states from n equals 0 to infinity. 0 is the ground state. And explicitly, you can also write down how this Fock state can be created from this vacuum state. And you get this basic algebra of creating a state and annihilating a photon and adding a photon, you get these prefactors n+1 and the square root of n. And on vacuum, of course, the annihilation operator annihilates the vacuum because there's no photon to annihilate. So that is a single mode. And we have a single annihilation operator, A dagger in A. And also we have a single quadrature operator of position Q and a single momentum quadrature operator of P. But let's say you have an n mode system, meaning you have n harmonic oscillators. And later we are going to talk about how they interact. But let's begin with the basic notations. You can essentially have all these quadrature operators in pairs. Each one represent a single mode system. So this is mode 1, this is mode 2, and this is mode n. And for simplicity, we write this as a vector, and we call it X vector. And we are omitting the vector hat, vector notation. So sometimes people might write that, but we're omitting that. Hopefully it won't create confusion because it's from now on, we are going to use X all the time, and it's always a vector. And you can check that the original commutation relation between all the P and Qs can be written in this vector form as well. And this is nothing but just, let's say, Qi P J equals delta Ij I times H bar, which is 1. So this means that the operators between the same oscillators will have non-zero commutators. But if you have operators from different oscillator, different mode, they're always commuting because they act on different subsystems. So therefore, we have this abstract notation. And this omega is often referred to as the metric of this system. And sometimes we call this a symplectic metric because later if you're coming from the math background, you will see this is a symplectic transform, all these unitaries that we care about. And this is the minus one appears because if you have a P in front, then it becomes a minus I. So this is actually saying Q and P is 1 and P and Q is minus 1, and they are in pairs. So this is a block form of a matrix. Right. So we'll follow the previous approach, start from unitaries, because if we include everything, when photons propagate, include all the things the photon can interact with, it's always a unitary. So a unitary dynamics is generated with a Hamiltonian, right? H in this case. And here we are talking about harmonic oscillators. So you can write down H in terms of quadrature operators P and Q. So you might learn about a basic quantum mechanics about these particles in a potential. And in that case, you are also describing Hamiltonians like P squared plus a VQ, where VQ is your trap. And that's also a special case of these Hamiltonians we're going to describe. And in general, we can always do a polynomial expansion, let's say a Taylor expansion of this potential. And in some sense, all these Hamiltonians eventually can be approximated by a polynomial of P and Q. So what we call by Gaussian is those polynomials that are lower or equal to 2, meaning that if you have a H bar, the Hamiltonian generated by P squared, Q squared, and their multiplication P and Q, or Q and P, and no higher order terms, then it's called Gaussian unitaries in this case. And non-Gaussian unitaries will be anything that are higher order in P and Q, like P squared, Q squared, cubed, P cubed, Q cubed. And Gaussian unitary is nice because in a few slides we are going to explain, but mathematically, Gaussian operations are just coordinate transforms of these vectors, of vector operations. So for now, let's just take this for granted. Later, we will explain why. So here I'm missing a dagger, I believe. Yeah. Okay. So to evaluate this, you can use this so-called Hadamard lemma, which is coming from algebra. So EA times B times e to the minus A is given by this commutator and nested commutator, and the nested commutator. It's a long formula and never ends, but if you happen to have a second order Hamiltonian, you can show that it always stops at a certain level. I think it stops at this level, or maybe this level.
Yeah, that one. Yeah.
So what you can do is that, okay, how to show this is actually a coordinate transform. What you can do, you can input that Hamiltonian. So think about e to the iht and x e to the minus iht. And now you're dealing with h and x. I'm omitting the t and I for now. So what you're going to have on the output side from that formula is you have an x from the first term plus the Hamiltonian commutation with x plus Hamiltonian and x, and this goes on. So if you put in q squared, p squared, whatever, if it's second order and you commutate with any q, for example, let's take this one. If it's p1, q1, and q1, you're going to have p1, q1, and q1. And this is going to be a number. So whenever you do a commutator between a polynomial of p and q and a single operator of q, you lower the order of polynomial by 1, and it becomes q hat. Then if you go to the next step, now you will only have numbers because q and p, they commute or they they commute or they don't commute, they will give you a number. So therefore it stops at this layer. So that's why then this is a number and this term is linear in x and this is x. So therefore everything in the end is going to be a linear transform of x hat to a new operator x prime. And in general, you can write this as a linear transform like this. Yes, I'm missing the I and T because they are going to be just factors you can put into it and fixing all the factors, but it will going to be linear in the end. I didn't write out IT for simplicity. Okay, so let's take examples. Let's begin with linear Hamiltonian of displacement. And you're going to see explicit examples of that linear transforms. So let's begin with this displacement, which are very common when you learn quantum optics. You might heard about laser, and laser is very useful in common life and also in experiments. And they are described by the so-called coherent states. And mathematically, they can be generated from vacuum state by a displacement operator. So displacement operator is very closely connected to lasers that you can use. And mathematically, this Hamiltonian is generated by just first order polynomials in P and Q. And you can have the two equivalent ways of expressing things. And you can verify this by the relation of A equals square root of 2, where Q is the real part and P is the imaginary part. And you can also do the reverse. Q is the real and the P is imaginary. And you can verify that this operation is just shifting this annihilation operator by a constant alpha. So this is the simplest case of these Gaussian operations. Nothing acts on this X, but just plus a constant. So let's call this C in general. And okay, here you might know that I'm writing things in annihilation operator. So how about this X hat, which is Q and P? Well, if annihilation operator A is linear evolved, of course, P and Q are linear evolved because they are the real and imaginary part of this annihilation operator. So you can essentially, so in the multimode case, then this, okay, I actually write out the vector, that's good. So these vectors are going to evolve, but also similar to here, because the multimode case, this operator D, C, is just a product of single mode operators. So therefore, it just shifts each mode by a constant, and therefore overall it shifts the global system by a constant vector. And a mathematical fact is that these displacement operators, they are orthogonal and complete. It's analog to Pauli operator. If you actually learned quantum mechanics or in quantum information, mostly relevant to qubit systems, you might know about Pauli operators, and Pauli operators form a complete basis for operators. And here, this displacement also form a complete operator basis. There's a question, what's the effect of the annihilation operator on a physical system? Well, earlier we know that annihilation operator will take away one photon from you, and you cannot act a single annihilation operator on a system because it's not unitary, right? So you have to think about these displacement operations. Well, one exception is that you can do a so-called photon number subtraction operation, and that is going to be probabilistic and not a unitary. Of course, you can also describe that by unitary, but we're not going to that details. Okay, Anthony might cover that later, actually. Okay, we're continuing. Isn't it overcomplete? Yes, it is. Just like coherent states are overcomplete, this is sort of overcomplete. Well, it depends on what you mean by overcomplete. From here, we still find these delta operators, right? So trace of two operator is delta, so it's not overcomplete in that sense.
An operator basis. What you probably refer to, Matthew, is the coherent states.
Yeah,
that's an overcomplete basis of states. It's overcomplete because they resolve the identity, like what Quntao just wrote, but alphas are not orthonormal.
Yeah, so alphas are not orthogonal to each other, alpha and beta, but the operator, they are orthogonal to each other, just like right down here, that's a delta function. So in some sense, yeah, they are complete and they are orthogonal, but not orthogonal in the sense of states. So what do we do? Well, if you ever have an orthogonal complete basis, you always want to use that to describe something. Let's say you pick a orthonormal basis of the eigenbasis, then okay, all these Hamiltonian analysis can be done in the orthonormal basis. Everything is simpler. So here, if you ever pick a orthonormal basis, you expand things, right? So this is the Wegener characteristic function. So take any operator A, you can do the trace of the displacement operator, and in a multimode case, then it's a multimode displacement operator. And then this will become the Wegener characteristic function. And then if you do a Fourier transform, pretend that this is a function. So this might pretend to inverse this function, then you get this Wegener function. And they are very useful in practice, as we will see. So now let's recap on Gaussian unitaries. So as we explained previously, these unitaries, Gaussian unitaries are described by some coordinate transform, and in general, it's a S, sort of a matrix that applies on this X, scales things, and then a D that shifts things, shift these operators by a constant. So if you analyze these Gaussian operations acting on this operator, from here, you immediately see that it's sort of a coordinate transform in the sense that the characteristic function evolves like a coordinate transform plus an extra phase. And moreover, the Wegener function it's actually just simply a coordinate transform. Here you see. So if I have a unitary that is a Gaussian unitary like here acting on this operator, it just transforms the Wigner function to the same Wigner function, but the coordinate is slightly transformed. So Gaussian unitaries are coordinate transforms in phase space. And by the way, this orthogonal basis we just built up is called the phase space of Wigner functions. And you might have learned that from basic quantum mechanics.
Or maybe in classical mechanics also.
Yeah, it also happens in classical mechanics when you learn about particle motions. You have P and Qs, you build a phase space, and the thermalization and all these things can be nicely described in phase space. So Gaussian unitary phase rotation. So we've learned displacement. So now let's learn about the unitary phase rotation. So now it's a second order unitaries. So A dagger A. You can also write down P and Qs. You just put it into the representation of P and Q into it, and then you get a second order of P and Qs. You can verify from that formula we have, like A is A, B e to the minus A equals B plus whatever commutators. From that, you can verify this simply rotates A by a phase vector e to the I theta. So in phase space, if you look at the Wigner function of this state, if you act this phase rotation R on it, by the way, this R is generated. What do we mean by this Hamiltonian and right on the unitary is that this R theta is generated by that Hamiltonian H theta, like that. So if you act this unitary R on a quantum state, this is unitary, so you can actually act it on quantum state. It will rotate this Wigner function in phase space by angle theta. So that's called phase rotation. And this is a single mode case. Multi-mode case, you can take a product of all these rotations, and then it's a multidimensional rotation. And why is it useful? Well, this is actually modeling this so-called free propagation. It's just a phase shift, meaning you might have heard about this interferometer where you have a beam splitter, which we will describe later, and you have different paths. Let's say this is path A and path B, and within this path, they're just free propagating in fiber or in free space. Then what's going on is that they are just described by a phase shift. So different path lengths will give you a phase. So there's a particular relation between the phase and the path length by dividing by the wavelengths and multiply 2 pi. So that describes free propagation. Okay, so that's phase rotation. And now here we go with the beam splitter, which is also useful. Like interferometers, it always have a beam splitter there. So mathematically, there's one extra. So it's generated by Hamiltonian A, B dagger plus A dagger B. And through that mathematical formula we have in earlier, you can verify that this will transform A to a mixture of A and B. It's a coherent mixture. And B becomes cosine B minus sine A. If you look at this looks like a rotation on a 2D system, cosine, sine minus sine in some sense. And this models beam splitter, of course. In your quantum optical lab, you have a beam splitter that actually have a 2 input light beam, and you mix these 2 beams and have the output, and they're described by this process. And Anthony will describe about what this does to single photons later on. And also we can have just very similar to beam splitter, but we put daggers on the same side. So this is so-called a 2-mode squeezing operation, A and B, and A dagger, B dagger. And this is useful because it generates the so-called 2-mode squeeze vacuum, or in some cases, people call it a spontaneous parametric Dunn conversion. Essentially what happens is that it's a Hamiltonian described by this A, B, A dagger, B dagger. And from that formula, you can also derive, okay, now A becomes A and B dagger, and B becomes B and A dagger. This dagger part is describing that there's actually amplification. So there's actual noise coming from the dagger part, which we will see later. So I would like to mention that this so-called two-mode squeeze vacuum by acting this two-mode squeezing on a vacuum is actually a bosonic analog of so-called EPR state. EPR state is like, let's say, a Bell state for the simple case. So a Bell state is in the Bell case, in the cubic case, it's equal to position of 0, 0, and 1, 1. If you write down this two-mode squeeze vacuum state, TMSV for two-mode squeeze vacuum, in a non-Bragg basis, you're going to see this coefficient Cn, and this sum from 0 to infinity. So the lowest orders are 0, 0 plus 1, 1 plus, and they will be higher order 2, 2. So in that sense, it's analog to a Bell pair. And there's also other ways you can do an analog between this and the EPR state by looking at the quadrature variances. We will not cover it here. Okay. Okay, now we go to non-Gaussian unitary. So as we said, Gaussians are second order, but non-Gaussians are going to be higher order. So for example, Q to the third or P to the third, it's cubic phase gate, cubic because it's third order. Phase gate, it's because maybe it's analog to actual phase gate, which is linear. And non-Gaussians also have this so-called Kerr nonlinearity. This comes from this number operator squared, where number operator is A dagger A. So you will see that it's A dagger A, so it's a fourth order. And this comes from nonlinear optics, where in classical nonlinear optics, when you expand these interactions, the linear order is n, and the second order is n squared. Third order would be n to the third and plus. You can expand this, and there will be coefficients in front. And the first order is a phase rotation. Second order now is a Kerr nonlinearity. How to write down H of beam splitter and the squeezer? Okay, so here this is H. This is the H, the Hamiltonian of. Okay, you might be asking about how to write this down in P and Q. You can essentially put in the relation between, well, this is Q1 plus IP1 divided by square root of 2. B equals Q1 plus Q2 plus IP2 over square root of 2. And then you input this, then you get the squeezer Hamiltonian in P and Qs. And then you get the unitary, which is e to the IHT, or sometimes you call R. Okay. And maybe before we go to the channel, we just briefly comment that if you just have Gaussian unitaries, it's not universal for quantum computation in the sense that you cannot generate these Kerr nonlinearities. You cannot generate this cubic phase gate, for example, just from second order Hamiltonians. And you would need at least one component coming from this non-Gaussian unitary to be universal. And people develop non-Gaussian resource series to emphasize that and to actually analyze how much non-Gaussianality is needed for completing certain computation tasks. But we're not going to cover that. So now finally we go to Gaussian channel. So a unitary channel is just a unitary. So for example, displacement channel, we have a U alpha acting on a state in the U alpha dagger. And this just shifts x to x hat plus some vector c. Okay, let's omit the hats, the vectors. So c. And of course, there's more. But maybe let me emphasize how to realize that displacement channel in experiments. You can have a beam splitter, and then you have let's say a strong coherent state, and then you have arbitrary state input. And now this beam splitter makes a high ratio of the state. So 1 minus epsilon portion of the input is going through here, while epsilon portion of the coherent state is going through. So if you let epsilon multiply alpha, okay, let's call it the beta, because alpha is the displacement we want to implement. If you let this beta times epsilon equals alpha, then you're going to shift this mean by a constant. And if you let epsilon go to 0, then you almost doesn't change the other property of the state. So then you realize this displacement channel or displaced unitary. Okay. What about thermal loss channel? So now we understand all the unitaries. The channels are just looking at a smaller part of it. So essentially, we can essentially stop here. You can do all the analysis, but let's just carry out some of the analysis because this is a lecture about the quantum channel. So thermal loss channel, you might recognize that it's just a part of the beam splitter, right? So the beam splitter has these two parts, A becomes A plus B, B becomes B plus A. If you look at one of it, then you just look at A prime, it becomes A plus E, where E is the environment system. And in general, thermal loss means that the environment system E can be in a thermal state, which has the photon number NB. And we denote this channel as a L, eta, NB. Eta is the transmissivity, and NB is the thermal noise level. And this models light propagation in a fiber or in free space when there's actually noise. So for example, although in optics, noise is very small, but there's non-zero noise in environment. Or if somebody is injecting noise into the fiber to jam your communication, or maybe you have some other, so a lot of people are sharing the same fiber, then other people's photons are like noise to you. So this is describing this process. All you need to understand is this beam splitter so that you understand this thermal loss channel.
Okay.
And of course, you can write out the, oh, this is second pole.
Yeah. Will you clear the?
Yeah.
Okay. So yeah, let me go over this. So a pure loss channel is when the. Can you go back to the previous slide for just a second? So we'll discuss a pure loss channel and that pole. So pure loss channel is when the environment mode E is in a vacuum state. There's no thermal photons. So you can think of this parameter eta as just an attenuation of your input. So if you have some intensity, if you have some light intensity with intensity I, it gets attenuated by eta. So eta is some parameter like less than 1. Okay, we go to the next slide now. Are all yeah. Okay, so just as in we described quite generically about the Krauss operators, like a Krauss representation for a quantum channel, sometimes called an operator sum representation. You can provide a Krauss representation for a pure loss channel, and it looks something like this. So don't worry about where this form came from. So the equation 1, that's a general Krauss representation, and then equation 2 is the specific case of pure loss. And so here's a pretty simple, well, you have to think about it a little bit, but here's a question. So consider the Krauss representation there and those Krauss operators, and consider that we have a single photon input state. Okay, so we have an input state with only one photon in it, right? So how many Krauss operators do we need in order to describe the output of the pure loss channel? And note that in equation 1, we technically need an infinite number of Krauss operators, but we're only dealing with a single photon state. And a pure loss channel is that you're losing photons. So yeah, that's the question. So how many Krauss operators do we need? And then let me pure loss and erasure. Yeah. So let me launch the poll. Okay. So there we go. And again, hint, you can focus just on the AL term and recall that, A really lowers the photon number. So we're losing photons. So we have a single photon state input, and then we're losing photons. So given equation 1 and 2, how many Krauss operators AL do we need? Let me give you guys about 30 more seconds. You have to think a little bit carefully about the answer. Okay, I'm gonna go ahead and close the poll and share the results. Okay, so most people, just barely most people said A, which is wrong. The actual answer is B. So 46% of the participants got that right. And we can explain why that's the case. We go to the next slide, Quntao. And yeah, so like I said, focus on just the AL term. So you'll have, I'll draw a little bit on here. So what you're looking at is terms like this, acting on your single photon state. So the A equals 0, the L equals 0. So L equal, L 0, that goes like, there is no A dagger. I mean, there is no A hat operator. There's just some, basically the only operator portion is this. This does nothing to your state. This really just adds a constant. So we will have the first cross operator. So definitely is 1. We'll definitely have 1. But the next one, L equals 1, this is proportional to A. So A lowers the photon number. So if A1 acts on a single photon state, what that'll take you to is the vacuum. Okay. So if you have higher order, so let's say you have 3, so let's say you have L equals, if you have 3 cross operators, L equals 2, any higher terms, because A annihilates the vacuum, will give you 0. Okay, so you really only need the first 2 cross operators, the L equals 0 and L equals 1. You need L equals 1 because you can lose a photon. The L equals 0 doesn't really do anything to your state, and the L equals 1 gives you photon loss. So that's why there's 2 instead of 1, and these are explicitly given by these formula down here. So again, yeah, this A naught, it basically says do nothing, okay, with some probability eta. You can think of it that way. And then the A1 is like lose a photon with some probability 1 minus eta. So you need 2 cross operators. Okay.
Great. So that's essentially explaining, okay, if you have a single photon, then this bosonic channel of a beam splitter, you can interpret this transmissivity eta as a success probability of transmitting that single photon through, and 1 minus eta is the probability that it will be lost and replaced by a vacuum. So also you might wonder how to solve these cross operators. We don't have time to cover that, but of course it's starting from the unitary, which is the beam splitter, which is e to the I, A B dagger plus B A dagger or minus. And then you can think about what basis to write down. Let's say write down certain basis En and on U and E0. You get that. And you might try, okay, I might do a, essentially I can Taylor expand this whole exponential into polynomials of A and B's and A hats and B hats. And then in numbers basis, then I can deal with all these mathematics, and then you can arrive at this. So we're not going to all the mathematical details here. So there's a question. You're considering short and squeezed noise as separate. I'm not sure what does that mean. Here, nothing is squeezed. Here, some people might know this is a short noise, so vacuum noise if you have a loss. Nothing is squeezed for now. Okay, so Gaussian channel, let's continue. Now let's do thermal amplifier channel. So thermal loss channel is coming from thermal, a beam splitter on thermal state and input state. And technically, if you want to purify the thermal state, you can purify it to a two-mode squeeze vacuum, but that's not often needed. But in thermal amplifier channel, it's now a two-mode squeezing instead of a beam splitter unitary. So this, if you remember, the two-mode squeezing maps input out like here. So square root of GA and B dagger and B A dagger. If you look at one of it, then it just becomes that expression of this amplifier channel. Why it's called amplifier? Because this square root of G here, G is greater than 1. So then if you have a classical coherent state, the output will have a larger amplitude of the coherent state, and of course plus some noise. So this is called a thermal amplifier, and this is G, square root of G minus 1. And then E hat, E is MB, which is the thermal noise. And in general, we can write this channel as a amplifier A in a calligraphic font, and G is the gain, MB is the noise level. And these are the two typical channels so far. We have thermal loss and thermal amplifier, and their vacuum limits in the sense of MB equals 0 is the pure loss and the pure amplifier channel. And there's a third case, which is called the additive Gaussian noise, meaning if I have a noise being mixed in, but a noise being mixed in, if it's related to the level of noise, level of transmissivity I have, then if I take the eta equals 1 limit, the noise of the environment is going to infinity, but the portion it gets mixed in is this, which is constant. And eta equals 1 means that the amplitude doesn't decay. So it becomes a so-called additive noise channel. And it can be also interpreted as a random displacement. So if you have input, if you do Gaussian distributed random displacement, it forms this so-called additive Gaussian noise channel as well. So these are the three basic channels you will need to consider in Gaussian channels. There were other channels like the complemental to this thermal amplifier, which is looking at the environment, but essentially it's coming from similar unitaries. So finally, one thing that we need to understand is how these channels can concatenate together, right? So in modern optical communication, if you have an optical fiber, then once in a while you have an amplifier to amplify the signal, and of course unavoidably add noise. But the classical case, it's okay. Quantum case, it's not. So quantum case, there were so-called quantum repeaters useful for quantum networking. But let's start with what happens if we have a loss and then amplifier, or if we have two loss, right? So if you have a one fiber connecting A to B, and then another fiber connecting B to C. So what's the overall channel from A to C? So this is the concatenation of two thermal loss channel. And you can derive this concatenation by this linear improper relation in these annihilation operators. And that's most of cases we derive channels in this form if it's a Gaussian, because it allows us only to look at these first order and second order correlations of field operators. So the first channel is going to map input mode A. So A is input to this A prime, which is the mode in the middle. And it's mixing this environment E1. And the second channel is going to take A prime as the input. So you just plug in this input relation. And of course, eta 2 can be different from the first eta 1. Now you just plug this A prime into the second formula. You get the overall input output relation from A to the final output A double prime. And just like intuition, if you have a property of eta 1 getting through the first channel and the property of eta 2 getting through the second channel, then the property of getting through the both channel is eta 1 multiply eta 2, which is intuitive. And the second part is we can define a third mode, E3, that combines all the noise modes together. You can verify mathematically that this is correct. And now, if you look at this form, it's again a thermal loss channel. It mixes this input A with a general thermal mode, although it's now defined as a mixture of the two thermal modes in some way, but it's still a thermal mode. So overall, it's a thermal loss channel. And this overall channel, it can be expressed by this, the channel emissivity is eta1 times eta2, and the thermal noise, you can calculate N3, which is E3 hat E3, which equals this expression. So the concatenation of two thermal loss channel is still a thermal loss channel, just with different transmissivity and different thermal noise. So this means that in a fiber network, if you look at any two nodes, if nothing else is going on in between, then it's always a thermal loss channel. Now let's think about the amplifiers, because amplifiers are always necessary in classical communication. So we can consider different ways of concatenating. We can have a thermal loss first and then amplifier, or can have amplifier first and thermal loss. And the analysis is very similar. So just like a previous case, we can derive the overall input-output relation. So the original input A is now mapped to A double prime, but with additional noise here. And this coefficient is a multiplication of the original gain and amplifier. Oops. And so there will be different cases now, because if you amplify too much, then the final state get amplified. If you amplify too little, then the final state is lost. So if G times eta is smaller than 1, overall it's a thermal loss channel. And you can also derive this N3 by calculating the photon number of this environment. And this is equals one case is the additive Gaussian noise channel, where you can derive this noise level. And G times eta greater than 1, it's a thermal amplifier channel. And you can also derive the formula. So I'm not going to follow this derivation, but all derivations are done in these linear transformations, which are like just like linear algebra, but you're doing linear algebra with quantum operators. That's the only difference. So now we do the exercise 1. Yeah, Anthony, do you want to do this?
Sure. Yeah, so I added these. I just added a few of these little exercises that are meant to be a little bit more in detail than the polls. But this is like a useful thing. Like Quntao said from before, you can have, for example, if you do loss and then amplification for eta G equals 1, you can have additive Gaussian noise. And a useful thing to know is that, yeah, so that's this. So from the previous slide, if you have loss, which is this L, and then amplify, which is A, and you have the gain and the loss satisfying this, you'll get an additive Gaussian noise channel with this number of added quanta into it. What you can actually show is that if you do the reverse process, if you first amplify and then go through a loss channel, again, you'll get an additive Gaussian noise channel, but with a different number of quanta in B2. And what's something nice that you can show is actually, if you do this reverse process, then you'll get less noise by first amplifying and then losing photons. And this is just a little useful thing to know about channels. It's came up recently in research projects, and people use it to, for example, discuss like quantum capacities of thermal loss channels or additive Gaussian noise channels and so on. And so you can prove this directly by using this sort of input-output relations that Quntao was just talking about. For example, if you have an input A, so this is for amplifier then loss. So if you have an input A to an amplifier channel, what you'll get is this output A prime, okay? So it gets amplified by gain G, and then here you have E2 dagger E2 is equal to some number of quanta N2, okay? And so then if you send this A prime, which is the output of the amplifier, through the loss channel, which you can derive as this A double prime, and which has this form, this just looks like this beam splitter stuff that you saw before. And if you write out this entire thing, what you can find is something similar to what Quntao showed on the previous slide, is you have this product, A to G, and then you have this bit over here. And from there, you can pick A to G goes to 1 and show that the amplifier then loss has a number of thermal quanta, which goes like this. And from there, you can show a simple relation that amplifier then loss is less noisy. You can go through this in detail, just using these little input-output relations, and then basically just measuring, for example, let me erase a little bit. You can use these little input-output relations, and then seeing how many quanta are in this little circled bit here to find NB2. So like I said, this is just a little useful thing to know about channels and playing with channels. Yeah. Okay, so let me clear.
Great. So now we go to single photons, and Anthony is going to cover the rest.
Okay, so I'll say next slide a lot. So
yeah.
Okay.
Oh yeah, next slide.
Is this the? Okay, yeah. So we'll just start from here. So single photon encodings. So a lot of photonic quantum information processing, encodes like quantum information into a single photon.
Okay, 1 second. Somebody's asking for a 5 minutes break. I think it's reasonable to have one.
Yeah, that's actually good.
Yeah, yeah.
Yeah,
So
sure.
let's have a 5 minutes break, and we'll be back in 5 minutes. Meanwhile, if you have questions, we can also answer them.
So we'll start back at 2:40. Well, that's 2:45 my time. 5 minutes.
Yeah.
Okay.
Okay, there's a question. How do we know H proportional to A B dagger plus A dagger B from scratch? Most books direct write this down without saying how to get this. Okay. Well, there's always something you begin with describing this. So there's a physical process of a beam splitter, and then you model this. Okay, where does this start with? Okay, one way to understand this, you're not going to derive this because this is a model. So there's always one step where you write down an initial thing and describe it. So there's no reason why this should be that. But to understand why this is proportional to that, you can think about it's like you have a beam splitter, you have 2-port input. If you annihilate one photon in A port, then you create another photon in the B port. So it becomes A B dagger term. And similarly, in the A dagger B term, you annihilate a photon in the B mode and create another photon in A mode. So this is why it's like that. Well, if you come from a physics background, then you understand things from experiments to begin with. So physics is still an experimental subject. So in experiments, people observe this phenomenon of photons disappearing and appearing on the other port. And then A dagger B and B dagger A is a mathematical model for it. And the way you model it is coming from experimental observations. If you come from the mathematical point of view, then, okay, I'm always allowed to write down any form of Hamiltonians, and this one, A B dagger and plus A dagger B, happen to describe what's going on in experiments. And yeah, that's the beam splitter. Oh, Anthony, you're muted.
Oh, sorry. Yeah, so also that Hamiltonian preserves the number of photons, the total number. So if like you have some environment modes and some system modes interacting, what they're really doing is just swapping quanta. There's nothing being generated. It's just quanta are being moved around during this interaction. And so that's also why that's useful. We'll give it about 2 more minutes. Channels for detection as well. You mean like photo detection?
These are measurement operations, and they are in general, depending on how you understand it. That's the case where I'm saying the measurement is the only thing that is not like a unitary. So you can understand the measurement in different ways. If you know the measurement result, then it's a post-selected event, and it's not a unitary. And if you don't know the result, then measurement is just some channel that projects in the basis. So yeah, measurement can also be described by channel, but in the sense that you are an observer, outside observer that don't know the measurement result. For example, if you have a photon number counter and I have an observer that is outside of this lab, all he knows is that one photon count has been done and he doesn't know the result. Then the channel is like a projection into the photon number diagonal basis. So you can write down something like that. And this would be your output. And you can check it's a linear quantum channel and produces photon number diagonal states. But if you are observer inside the lab, then you know the measurement result K, then you know it's a photon number state afterwards. That's a post-selected quantum operations. Can we mix degrees of freedom like QAM in EM wave? Okay, I think Anthony is going to cover that. Yeah, so I think it's time to continue.
Okay. Like QAM. What is that? Is that quadrature amplitude? Not sure what QAM means.
It's probably quadrature amplitude modulation.
That's okay.
So can we mix degree of freedom?
Well, for quadrature amplitude modulation that's just amplitude and phase, right?
Mm-hmm. Yeah.
It's just like Q and P. I don't know if
So I'm guessing the question may be asking, yeah, photons have many degree of freedom. Indeed, you can use all of these. They are in tensor product structure if you write down the states. So you can use all of the degree of freedom to do things. Of course, they can be used together, but yeah. So that I think that's okay. Let's continue.
Okay. So yeah. So what we'll focus on from now on is the single photon encodings. So what we have in mind is we have some like quantum information. It's in some like logical basis of 0 and 1. So these are like bit values 0 and 1, and we'll encode them into a single photon state. And it's typically done in this so-called for dual rail qubits. So someone just mentioned degrees of freedom. So photons have many degrees of freedom. So they have polarization, spatial, angular momentum, etc. And each of these degrees of freedom can more or less be described by these independent sets of mode operators. So if you have 1 degree of freedom, you can describe it by a set of mode operators or annihilation operators, A sub k, where this k runs from 1 to m, and m is the number of modes. For polarization, the photon can only have 2 polarization states. So m is only 2 there. But for example, for angular momentum can run from L equals 0 to L equals infinity. So this can be an infinite number of modes, a large number of modes, or just a few modes. But we'll only focus on 2 modes. So no matter how large m is or what m, what the degree of freedom is, we'll just pick 2 of the modes out of the basis and define a photonic qubit from there. So we'll define logical states, 0 and 1 states of single photon, as written down right there. So we'll define the logical 0 state as being a single photon in the first mode. So this A1 dagger on the vacuum is equal to this A1 dagger on the vacuum right there. That's we'll define that as logical 0, and A2 dagger on the vacuum, we'll define that as the logical 1. So this is just saying that either my photon is in this k equals 1 or it's in the k equals 2. And for a general dual rail qubit, we'll have it's a linear combination of these 2 states. Okay. And I just want to say that, I write this in shorthand, but technically, this is the tensor product structure that Quntao just mentioned, is that when I write down vacuum here, it's really a tensor product of vacuums for the first mode and the second mode. And when I write down stuff like this, what I'm really saying is that you're creating one photon in the first mode and doing nothing to the second mode. So you can think of it as sort of two rails. I think that's why people call it dual rail. Is you have a first mode here and a second mode here, and you're occupying one of these modes or the other with a single photon. Okay, so that's this dual rail encoding. Yeah, next slide. Okay, is that?
Yeah.
Okay, so single qubit operations.
Yeah.
Yeah, so we have a single qubit. So the first thing that you might ask is, how can you do single qubit operations like Pauli X, Pauli Z, or rotations on this block sphere? I won't talk about the block sphere here, but we'll just talk about general single qubit operations. Turns out for dual rail encodings, all single qubit operations can be implemented with passive operations. And what I mean by passive is that these passive operations commute with the total photon number. Okay, so if you think about a single photon occupying one of these two rails, passive operations just push that photon to this rail or push it to the other. Okay, there's no photons added to the state. And passive operations consist of beam splitters and phase shifters. So Quntao mentioned these before. These beam splitter Hamiltonian between 2 modes A1 and A2 looks something like this. Okay, and this theta here, let me just mention this cosine squared theta is basically just the probability to transmit through this beam splitter or not. Okay, and then phase shifters are of the form like this. So this is like free evolution. It just puts a phase. So the phase shifters, again, they'll take A1 to e to the I phi 1 A1. Okay. Okay. Oh, next slide. Okay, so this is just a little exercise. So you can show actually that any Hamiltonian of this form, which kind of looks like a dagger A, commutes with a total photon number. Okay, so what I mean by that is H big N is equal to 0. You can show this. And this is really just equivalent to showing this thing that I have up here, that each of these individual terms in the Hamiltonian actually commute with the total photon number. So I actually have it written down slightly different, but that's okay. A dagger, AJ. So these are the individual terms in the Hamiltonian. And I actually will write this out explicitly just for you guys. Commute with the total photon number. The total photon number, AJ, AK dagger, AK is equal to this. Okay. You can use this little ABC rule that I have here to pull operators out to the left and right. This is this is just you can check this, that the commutator satisfies this. And so what we have is we have AI dagger, AJ, AK dagger, AK plus AI dagger, AK dagger, AK, AJ. Okay. Again, you can do a similar kind of thing for this. What you can note is that AJ, you can use this ABC rule again to simplify this. AJ will commute with AK, okay, but it will but AJ with AK dagger will give you a delta function. So actually this part will be actually be AJ AK dagger AK, which is equal to delta JK AK. Okay. And so, and similarly, you'll get the same thing here. You get a similar thing here, but this will come with a minus sign. So with minus sign. Okay. And then just writing it down, finally, the last line, this is AK AI dagger, AK delta JK plus AJ. Oh, that's supposed to be minus AJ. And this will come with an A. Yeah, that'll come with an AK dagger delta IK. And then, yeah, and then that's it from there. So these delta functions reduce the sum. And so you have AI dagger, AJ, and then oh, sorry, actually I wrote this wrote the second term wrong. So this is supposed to be AK dagger AJ. Yeah, there we go. And then yeah, so these go away. So any Hamiltonian that can be written in this form up top commutes with the total photon number, and that defines a passive operation. Okay. Okay, so next slide. So in particular, Quntao mentioned this before, this beam splitter kind of acts like a rotation. So here what I've written down is actually a generalized beam splitter. So you have a phase and you have a probability to transmit through the beam splitter, which is cosine squared theta. But then you also have this extra phase. You can get this from physically from a Mach-Zehnder interferometer, which a Mach-Zehnder interferometer looks like this, where these beam splitters are related to thetas, and then this phi is the phase in between, which you can generate from, for example, by changing the path length of one of the arms. And so the action of a general beam splitter is this rotation matrix below. It's actually just a unitary matrix. So yeah, it's a unitary with the determinant 1. And you can easily show in this representation that logical states under this generalized beam splitter transform in this way. So you can generate, starting from 0, you can generate, these qubit states starting from this by applying this generalized beam splitter on your single photonic qubit. Yeah, thank you. So here's a little poll. So Pauli X of the beam splitter. So consider 2 input modes to a general beam splitter that I showed on the previous slide. And this is given like this. And the question is, up to a global phase, can we implement the Pauli X matrix with this beam splitter? And what I mean by this is, so if I call this VBS, does there exist theta and phi such that VBS is equal to this Pauli matrix, maybe up to some phase, some global phase we don't really care about, e to the I big phi. And it's a simple question, yes or no. So let me open the poll. Let me go ahead and launch the poll. Okay. So I'll give you about a minute and a half to answer this, since it's a simple yes or no question. There's about 30 seconds left. 40% of people have answered. If you haven't answered, go ahead and put your answers in. Okay, I'm going to go ahead and close the poll. So anybody who's not answered has lost their chance. So let's see, share the results. Most people answered yes, and that is the correct answer. So let me stop sharing those results. We go to the next slide just so we can explain the answer. And yeah, the answer is yes. So if you choose, for example, theta equals phi equals pi over 2, and substitute those values into the rotation matrix above, what you'll find is that this matrix that I've written down with off-diagonal terms proportional to e to the I pi over 2, which is just I. And so the global phase here is just, e to the I pi over 2. Right. So yeah, you can implement the Pauli X with this generalized beam splitter. So you can go from the 0 state to the 1 state in this photonic encoding with some beam splitter. Okay, next slide, please. Here's another example. This is just more so an exercise. So consider these transformation matrices for the phases and beam splitters. Here's a question: is what combination of phase shifters and beam splitters produces the Hadamard matrix H? So this is one of these single qubit gates that people like in quantum information processing, called the Hadamard matrix. And using these transformations, you can't. I don't think you can do it with only a beam splitter. I think you actually need these extra phase shifts to implement the Hadamard, but you can do so with a combination of both. So, for example, choose phi 1 equals 0 and phi 2 equals pi for the phase shifter, so that the phase shift matrix is basically a Pauli Z. And then choose theta equals pi over 4 and phi equals pi over 2. So the beam splitter is like, it's basically some combination of identity and a Pauli Y. Then you can show that the product of these two matrices is actually the Hadamard matrix. So again, you can do a Hadamard matrix with the phase shifts and beam splitters. And this just gives you these are just examples of what I said before, that you can implement any single qubit operations with phase shifts and beam splitters on single photons. Okay. So that was quite, there's some quite general discussion about the dual rail qubits, but there's physical degrees of freedom that people encode in. And so, I mentioned these before: spatial, polarization, angular momentum. There's time bend encodings, all these kind of things. And but choosing one might be up to context or preference. And so some things you might need to consider is this degree of freedom easy to manipulate, right? Because you have to do single qubit operations. You might have to, interfere if you want to do large scale things. You'll have to interfere in multiple photons, etc. Is the degree of freedom robust to relevant noise sources? So that depends on your task. If you're doing like maybe something just on a chip, or if you're doing things through free space, those are different environments you have to deal with. And if necessary, can we scale up for quantum information processing with many photons? Is it easier to do in some degrees of freedom than others? And this, the answer to these will just depend on context. But we'll discuss briefly some common encodings that people use. One is this spatial encoding. So you have a photon with a fixed frequency omega, it has a fixed polarization, fixed angular momentum, everything else is the same, but it can traverse two different spatial paths. So an example of this is just, like I have two beams of light. One's going this way. It has some general, for example, K vector 1. Or I have a beam of light going this way with some K vector 2. So this defines two spatial paths that the photon can go on. And then you can just interact these. This is really like a physical representation of this dual rail qubit. Like you physically have a single photon in either one physical path or another physical path. And then you can interact these two modes by simply overlapping them on a beam splitter at the right time. Okay. And then the phase shifts that we were talking about before, this is directly given by the path lengths. So omega over c is just k, and then lk is just the length of the path. So phase shifts are given literally by just changing the path lengths. Another very common degree of freedom is polarization. So I mentioned before that photons can have different polarizations. So polarization, again, if you have a photon that's traveling this way, so it has a vector k. There's this two-dimensional plane that's perpendicular to k, which defines the polarization of the of the photon. So, and it can have different polarizations. Common ones are this so-called horizontal polarization and vertical polarization. These are two orthogonal polarizations for the photon. And you define logical states as, being in one polarization mode or the other. And how you implement single photon operations with these so-called birefringent materials that treat one polarization differently than they do the other one. So you do rotations and stuff with these birefringent materials. Okay. And then the last thing that I'll mention is so-called time bend encoding. So this is everything else is the same, but that the photon may occupy two different time bends, often called early and late. So basically, it's like a superposition of when the photon arrived. You can think of it like that: either arrived early or arrived at a late time. And to do things with this, you need to do operations with this. You need fast optical switches, because you're really playing with time here, and switches and delays to implement single photon operations. I'll give you a cute example of where time bend encoding is used on a paper I read multiple years ago. But people doing, for example, there's these satellite experiments where there's a satellite moving quickly over the Earth, and they're sending photons to the satellite, and then it's bouncing off. It's bouncing back off and landing at another time. And because the satellite is moving, when the photon hits the satellite, will imprint a phase on the light. But if it's in a superposition of early and late times, you can actually get interference phenomena due to the motion of the satellite. So people are doing sort of because these satellites are moving fast, like first order relativistic interference effects with single photons of light. So that's an interesting example. Okay, next slide. And you have all these degrees of freedom that you can deal with, but you can actually swap between them. So here's an example of swapping from polarization to spatial. We have a question. It sounds cool. Can we get a reference? It's from the Italian group multiple years ago. I'd have to look it up, but it's from the Italian space group. I think it's LIGOS. I might be wrong, but I think the satellite's called that. Yeah. Yeah, that's a cool paper, and people are doing a lot of experiments with satellites. There's a so-called Mishias satellite or Motsi satellite. There's this Chinese satellite, and they're using mainly polarization degree freedom. So that's a use case of polarization, because the atmosphere doesn't really change is not really birefringent, so it doesn't really mess with your photonic encoding at the polarization basis. Okay, so that's two different applications of polarization and time bend. Okay, so yeah, so here, yeah, we can swap encodings, and what you can do is, for example, swap from polarization to spatial. And one way to do this is through a so-called polarizing beam splitter that does the following transformation. So let's say we have two spatial modes, 1 and 2, okay? And a polarizing beam splitter does the following. If you're H, you go through, and if you're V, you get reflected, okay? So physically what this means is this little picture that I've drawn. It's easier to see it here. If you're over here and you're horizontal, then you get reflected. So you go here. If you're over here and you're horizontal, then you get reflected. So you go here, right? However, if you're vertical, let's say you're vertical, you're over here. I messed up. I said reflected a second ago. I meant transmitted. So if you're horizontal, you get transmitted. If you're vertical, however, and you start over here, then you get reflected to this down port. If you're vertical up here, then you get reflected to this side output port here. Okay. So how does that make you go from polarization encoding to spatial encoding? Well, let's say I have a single photon qubit, okay, that's in a superposition of H and V, but it's only going on one spatial path, right? So physically it's going on one path, but it could be in a superposition of H plus beta V, okay? Once it hits this beam splitter, it'll either go here, let's say it's a 50-50 beam splitter, they'll go here if it's if it's V, and it'll go here if it's H, okay? So then what we do is on this side we do nothing, but on this side what we do is we add a polarization rotation that takes vertical to horizontal. Okay, so now what the total output would be is yeah, we can actually write this down completely. H1 goes to AH1, AV1 goes to AV2, and then you put a polarization rotation here that takes V to H. So then your total output would be you have a single photon. It has a definite polarization H, but now you don't know what spatial mode it's in. So now what we've done is we've sent this polarization encoding. Instead, maybe I'll just call it path 1 plus beta path 2. So using this polarizing beam splitter, you can go from polarization encoding for your dual world qubit to spatial encoding. You can do similar things with the time bend, but again, you need like some fast optical switches to do that, because again, you're playing with time. Okay. Can you get the next slide, Quntao? Oh, hold on. Yes, you can entangle. Yeah, so somebody mentioned you can entangle polarization with orbital angular momentum. Some people call that hyperentanglement. Yeah, you can entangle many of these degrees of freedom. Actually, the thing I just showed you before that polarization rotation, what you have is many degrees. You have polarization and spatial intermixed, right? So yeah, that's kind of an example of hyperentanglement. Why would you want to switch between encoding types? So for example, this early time and late time encodings. So you might want to do that. Let's say you want to do some interference experiment, like I said before, with like a moving thing, and so you want to imprint the motion on your photonic state. But then later you want to do when it comes back, you want to do some operations on it or things like this. Operations in that particular early late time bend basis are hard. So what you might want to do first is go switch from time bend to polarization, then do single qubit operations, and then switch back from polarization to time bend, and then do your experiment. So that's an example of why you'd want to switch between encoding types. Hopefully that answered. That's just an example of why you might want to do that. What's the typical time difference and time encoding between the early and late modes? I have no idea. I honestly do not know. Anybody else?
Probably the shorter the better.
Yeah, it can't be
About
because you want to. Oh, go ahead.
10 to the -5 or 6. That's certainly doable, I think.
Yeah, you don't want them too short because these are wave packets, so you don't want them to overlap. So it depends on the temporal profile or the frequency profile. But yeah, I mean, maybe that depends on your switches as well, how quick your switches are. So that might also depend on what you want to do, right? If you want to do some like fast quantum information processing, then you might want it as short as possible. But again, that depends on your profile, your temporal profile, but also how fast you can do these switches. So that might depend on context. Okay, so that's encodings. Now I'll go through single photon evolution through Gaussian channels, and we'll focus on this the so-called thermal loss channel that we mentioned before. It's basically just like this picture that Quntao referred to. So you have a single mode. Well, it's not a single mode. You have a photon A that interacts with some environment. Here's just some sort of like random thermal noise. Interacts on a beam splitter with the transmittance eta. So this is transmission probability eta. And this is a very common one. And, I mean, most communication links, stuff like that, over noisy fibers or free space links, which can be accurately described by thermal loss channels. Okay. So, for example, the background quanta NB, so this is the thermal noise, comes from the population of the environment. For example, if you're doing like free space communication and the sun's out or the moon's real bright or you're pointing in that direction, then this background quanta comes from that noise source, the sun, the moon, or maybe even background lights. And then this loss probability, which is actually 1 minus eta, is equal to the absorption probability of the medium. Okay, so any medium, it won't just let you propagate through. There's atoms that are jiggling, atoms and molecules that are jiggling around that can absorb the light with some probability, and that's what this eta is related to. So an example is, given a fiber of length L, you get this eta. It actually exponentially decays with the fiber length, where this alpha is an attenuation coefficient. Typically is quoted in like decibels per kilometer. And the reason you get this exponential attenuation is a consequence of actually the so-called Beer-Lambert law for linear absorptive dielectric media. So that's where this exponential decay comes from. Basically, you can think about this. If I just said that in more detail, you can think about a wave propagating with a wave vector k tilde. But this k tilde is actually complex due to absorption. Yeah, maybe I'll write it like that. And then this leads to you have your free propagation, and then e to the minus alpha x. You have exponential decay due to absorption. Oh, that was the electronics. Oh, that's nice. So someone, Matthew is mentioning about this early time bin stuff again. He said my lab is trying to do this early late time bin with differences smaller than a few nanoseconds. The electronics are actually the hardest part for switches. So yeah, so that's the switching stuff. They can be smaller, but as described, the wave packet size must be smaller than the separation. Yeah. So yeah, that's thanks, Matthew. So that's cool that you guys are doing that. But yeah, so that's kind of what I figured is you have to deal with this wave packet size, but you also have to deal with these fast electronic switches to do single qubit operations and stuff. All right, thanks, Matt. Okay, next slide, please. Okay. So thermal loss, it actually emits a nice channel decomposition, which is useful to know. So a general thermal loss channel written here, L, eta, NB. So eta is the transmission probability and NB is the number of background quanta, is actually equivalent to a pure loss channel followed by an amplifier, which satisfies these relations. So tau G is equal to eta, and then the number of background quanta is related to this. That's not so important, but it's important to know that this decomposition is possible. I was going to write this decomposition in detail. I guess maybe I can. This actually won't take long. So the first thing is let's say I have an input mode A. So through a pure loss channel, this will go to A prime equals tau A plus 1 minus tau E1. And since this is pure loss, this E1 is actually not populated at all. Why did I write E2 there? This E1 is actually in a vacuum state. Okay. And then follow this, we have an amplifier, gain G, which takes A prime to A double prime, which is G, A prime plus G minus 1, E2 dagger. Or again, E2 dagger E2 is equal to E1 dagger E1, which is equal to 0. So yeah, so if you write this out, you'll have as G tau A plus Oops, something happened. Hold on 1 second. Something happened on my. Okay, there we go. Sorry, guys, something happened on my iPad. Okay. Anyway, so what we have here is we have G 1 minus tau E1 plus, so G is acting on that. That's fine. G minus 1 E2 dagger. And then what you can show from there is that, let me change colors real quick. You can write this whole thing as an E3 is equal to G 1 minus tau E1 plus G minus 1 E2 dagger over 1 minus G tau. Okay. And then using the relations above, what you can show is E3 dagger E3 is equal to, actually from here, it's just equal to G minus 1 over 1 minus G tau. Okay, and that's this NB down here. Okay, so that's how you would show, at least this little input output linear relations that this decomposition works. Okay, yeah, next slide, please. Okay, this is a little more complicated, but this is why that decomposition is useful. Okay, if you remember from before, you probably don't because it's slightly complicated. The Krauss operators for a pure loss channel are given by this complicated formula. Okay, you can also do you can also write down the Krauss operators for the quantum limited amplifier. So it's a bit similar actually to the pure loss. That's right here. But now we have a dagger instead of an A. That's because for the amplifier we're adding photons, where for the loss channel we're taking away photons. And then using these decomposition, it should be clear that the operator sum representation or the cross representation for the thermal loss channel is just given by a combination of these cross operators. And we'll use that to see how a thermal loss channel affects a single photon. Okay, next slide. All right, thank you. So now we'll consider a single photon input with the output given formally by this, and even more formally by this representation up here. So first of all, if we disregard the action of the amplifier, for these B operators, we only look at the A operators. Actually, this comes from an exercise previously, is that terms that go like this are only non-zero when L equals 0 or L equals 1. And what we have there is that the first term acts like this. So either the photon actually gets transmitted with some probability tau, or the photon gets lost with some probability 1 minus tau. Okay, and and it's just you get the vacuum. Okay, so next slide, please. Oh, so good time for a poll. Hopefully I just kind of answered this question for you. So let's ask this question. So when acting on a single photon state, rho 1, the pure loss channel, L tau, is equivalent to an erasure channel with erasure probability epsilon equals 1 minus tau. What is the erasure state in this case? Hint, note that we are losing photons via loss. So let me go ahead and start the poll. And this is the last poll question, by the way. So big sigh of relief. Yeah, so what is the erasure state in this case? Is it the starting from single photon state? Is it the vacuum state? Is it a completely mixed single photon state, so you just get a random photon? Or is it a state with greater than or equal to 2 photons? It's about 40% of people have answered. I'll give you about 30 more seconds. Put the answers in. If it doesn't come right to the top of your head, just make an educated guess. That's okay. About 10 more seconds. Okay, now I'll go ahead and stop the polls. So in poll, share results. So most people said A, so vacuum state, and that is correct. So let's see why. The answer is pretty intuitive. Will you go to the next slide, please, Quntao? Yeah, so explicitly, you can write down exactly how the pure loss channel acts on a single photon state, rho 1. So it goes like tau rho 1 plus 1 minus tau vac. If you remember for the erasure state, for some general state psi, it goes like this. So with probability epsilon, you get erased. Okay. So here, oh, did I write tau? Maybe I meant eta. Anyway, so this should be eta. Yeah, in any case, yeah, the erasure state's the vacuum state. Basically, you send the single photon through the loss channel, you either get the photon with probability tau, or you lose the photon with probability 1 minus tau. Okay. So next slide, please. Hopefully that should be fairly intuitive. So that was a little simpler thing before this more complicated mess here. Okay, so the pure loss case is actually pretty easy because, like I said, starting from a single photon, either you get the photon or you lose it and get the vacuum. There's really nothing after the vacuum. You don't go down on this harmonic oscillator ladder. But things become more complicated due to amplifier, because then you're adding photons and you can go all the way up the ladder to n equals, infinity photons. So that's why things get more complicated. But we'll focus on just a few of these first few operators for the amplifier channel, this k equals 1 and k equals 0. So the k equals 0 looks something like this. Basically, it's again, this is kind of like nothing happens, okay, with some probability. You can think of it like that. You're not gaining photons, you're not losing photons, so nothing happens. But the B1's a little bit different. Now we have this a dagger term. So that means, you can think about it like with some probability, we're adding a photon to the state, okay? And so if you take all of these combinations together, A0, A1, B0, B1, if you take all of these combinations together, then what you'll get is these following 4 combinations. So the 0, 0 terms, basically the photon is just unaffected by the channel, right? Nothing happens, it just transmits through. The second possibility is, the photon doesn't get lost, but there is an extra photon added to the channel. So you have 1 noisy photon added to your state. So now you have some state rho 2, which is just some 2 photon state, and there's a little bit of noise in there due to the channel. Third possibility is that you lose a photon from the pure loss part, and then nothing happens from the amplifier part. So in that case, this is similar to just pure loss. The photon is lost with some probability, right? And then we have this this 1-1 term, this fourth option here, and that's the photon is lost. So the photon that you input is lost, but now the amplifier part adds a photon. So in that case, the photon is lost and then replaced with a single noisy photon state, which this is coming from your background channel. So this is actually related to the NB number of photons. Okay, so for a single photonic qubit, this could be a completely mixed state in the single photon subspace in the dual rail qubit basis. Okay, next slide, please. So those are your possibilities. And if you combine all of those things together, then what you get for the output is a sum of these possibilities. So again, this first term, you get the single photon without a problem. The second term, you get a single photon, but it's not the photon you wanted. It's just some noisy photon. So, that's not good. Here you get no photons whatsoever. So this is like this is similar to erasure. And then here you get some state with greater than or equal to 2 photons. Okay. So this could be 2 photon, this will be 2 photon states, 3 photon states, 4 photon states, whatever. But this is just some state with greater than or equal to 2 photons. And so you can calculate, for example, transmission event probability. So this is the probabilities that you get these terms. This is important, especially if you want to know the success of some communication task like distributing photons. This also becomes important when you're dealing with more than 1 photon, like distributing entanglement. So the successful transmission, that's just this probability up here, this first probability. That's probability that you successfully transmit the photon. This is the probability that you get a random photon. This is the probability that you receive nothing. And this is the probability that you receive greater than or equal to 2 photons, which is just 1 minus the probability of these other events. Okay, and we've written them out here in these original variables of eta and NB of the channel rather than these like auxiliary variables of tau and G. Okay, so next slide, please. Okay, so this is a nice little example. And so those aren't very intuitive, but it becomes useful when you look at this low noise limit. And the reason you might want to look at this noise limit is if you're dealing with like single photons, you want to operate in the low noise limit to begin with, right? So you don't want many noisy photons leaking into your system. Like for example, if I'm in a satellite and I'm distributing photons to the ground, I don't want many background photons from the sun leaking into my signal, right? So I want to operate in this low noise limit. What you can do here, this is just a simple exercise, is that in this low noise limit, you can calculate all these transmission probability or these event probabilities. And one thing that you can calculate, for example, is this probability for a 2-photon event or greater than 2-photon event. So one of the questions is show that the 2-photon event is equal to this, and can we give an intuitive explanation for this result? One thing I want to mention, by the way, is that we have some lecture notes that go over a lot of deep details that we might have glossed over in the slides. And they also have these exercises in there that you can take your time with and do yourself. And there's also some references. So if the notes and slides aren't enough, then you can get some references. Yeah, thank you. And I think Brianna just added another link in the chat to those. Okay. So you can go through all of these little derivations. You just use Taylor series to expand these different things to second order and the number of photons. And then what you can find at the end of the day is that this 2-photon event has this probability. The explanation for it is fairly intuitive. Let me tell you why. This part, so this is how you can think of this part, why there's an eta and a 1 minus eta. Well, let's think about where these 2 photons are coming from. One is coming from the photon that you sent in, and another photon is coming from the source here. Okay, so what you need to happen is that you need this photon to get transmitted, and which that happens with probability eta, and then you need this photon to get reflected, and that happens with probability 1 minus eta, right? So that's why that happens. And you're only getting 1 photon from here, okay? You're not getting 2, and the reason you're not getting 2 is if you were getting 2, then you would have the probability of getting 2 photons from the thermal source itself goes like NB squared, and we're dropping NB squared terms. So that's why this eta and 1 minus eta term is there. The factor of 2, this has something to do with the indistinguishability of bosons. So there's some symmetry between the A and the E mode because these photons are indistinguishable at this beam splitter junction. So that's where this factor of 2 comes from. And then, of course, the factor of NB, if there's no thermal photons, then you won't get greater than or equal to 2 photons. So that factor has to be there. So that's an intuitive explanation of why you could actually probably guess what this probability is. Okay. Oh, so I guess that's about it. That ends our slides. That might be a little early, but that's okay.
We're a little early, but okay, we have 2 more slides, do we? 61 to 62, 63.
We have the recap and then this exercise.
Okay. Yeah, so hopefully in this course, we are able to convey the idea that photons are useful for quantum networking, and also it's useful for sensing, communication, and in some cases also computing. And we reviewed the how photons evolve in common scenarios like a fiber or open space link. These are all special case of a bosonic Gaussian channel. And in this particular case, there is a pure loss or thermal loss channel. And we can understand this by going to the unitary the unitary is essentially the interaction between this input and an environment. And the environment in this case is a thermal system, the thermal state environment. And so all these Gaussian channels can be understood by going to the unitary, which are Gaussian unitary. And then you can calculate the cross operator by choosing, for example, photon number basis of the environment. And then these cross operators are useful. Why? Because Anthony has shown that they can allow you to understand the evolution of single photons, because A dagger and A, they act on these photons, they create or annihilate photons. And these are the basic tools for you to understand how we analyze photon propagations. Here's a question. Do you want to say anything about how these operations are implemented or used? So I guess operations, meaning the Gaussian operations we have learned. Beam splitters are just, beam splitters. It could be different realizations. I think when I go to the quantum optical labs, a beam splitter just looks like a shiny cube to me. And in nanophotonics, it's like on a chip, two guides. So you have waveguides. These waveguides can interfere through some junctions, and then that will create a beam splitter. Squeezers are usually, like say, in cavities, it's a nonlinear crystal. On chip, it could be something else, but it also requires nonlinear operations, and that creates the squeezing. And for those models for thermal loss channel or thermal loss channel, you don't even need to implement it. So whenever you send a photon out, it's automatically a thermal loss channel. And what you do is actually how to fight against this thermal loss channel that happens in fiber connection or space link connection. How do you maintain quantum coherence? So that will need to have quantum error correction developed for whatever encoding you have. And then what's the rate predicted? These are answers you can obtain from the models of this channel. Would you please talk about the single rail optical qubits as well? What are main differences and the benefits between single and dual rail qubits? Yeah, Anthony, you want to take it?
I guess when you say single rail, I think people call it this Fock space encoding, where you have like the presence of a photon. I mean, the absence of a photon is the 0 state, and the presence of a photon is a 1 state. So that's in a single mode.
Well, they require different set of gates, right? So
yeah,
time being is nice.
Yeah, you need something more than, you can't do that with passive operations, right? Because to go from one, so this is what I mean. So you might call a logical state the vacuum. You might call a 1 state, well, n equals 1, right? But to go between these states, obviously you need to be able to change the photon number coherently. And so you need something more than passive operations, right? Because if you recall, passive operations commute with a total number of photons. But to go from the 0 state to the 1 state here, obviously you need something that changes the photon number. So you need coherent non-photon number preserving operations to deal with these.
There's also an analog to classical coherent communication. So there's on and off encoding. So if you send a vacuum, if you send the coherent state, that's on and off. Then in some sense, it's like single rail 0 and 1 photons. It's like on and off. But if you have other encodings, like if you know about this, it's what's that called? Position-based encoding. Like when do you send out the coherent state pulse will encode the classical message? Then it's like a pulse position modulation. That's something look like a time being in early or late, or you might generalize that to qubit. Then you can also think about that way.
Yeah.
Okay. Other than
a bit about also quantum error correction that we haven't went over, that people do in different kind of bases.
Mm-hmm. Other than the course notes, do you have recommended in-depth readings? But the course notes have some references. There's one review of modern physics by Wiedebrook, which is reference 3 of the course notes. That's a standard reference you can use to understand the continuous variable system and Gaussian operations. And there are other books and
okay. Oh, I can two hosts.
there's a Serafini book called Continuous Quantum Information, something like that. Continuous variable quantum information.
Yeah, I'll type a few. I'll type one in the chat that's more so so those are Gaussian. There's this nice little book on photonic quantum information processing by Peter Koch and I forgot his first name, something Lovett. But that's a pretty good book that goes over all these like different encodings and goes over dual rail qubits and a bunch of other things done with quantum optics and cluster states and all this other stuff. So that's one. And then like Quntao mentioned about just general Gaussian operations and Gaussian quantum information, this Rev Mod Phys by Wiedbroek et al. There's that one. And a Serafini quantum continuous variables. So there's some stuff on Gaussian and then just general photonic quantum information processing. They're like pedagogical.
One thing is that these books and or papers might be using different definition of H bar. H bar equals 1, square root of 2,
I've never seen 2.
Well, I believe the Wiedbroek paper have H bar equals 2.
Oh, really?
Okay. So you might be careful in terms of reading between different books. All these definitions of mean and covariance might have some tiny differences. And yeah, it's something to keep in mind when you read these different references.
Yeah, and so someone mentioned Mark's book. Yeah, Mark's book's really good for about general. The first part of the lectures are just about general quantum channels, Krauss operators, purifications, all this stuff. So the first I think 4 or 5 chapters of Mark Wilde's book on quantum information theory is good if you want to learn about that stuff.
Yeah, that book is very useful for quantum channel capacity. If you want to understand the communication capacity, quantum channel theory, that's a very nice book to read. Do you know what lab equivalence of a thermal amplifier would be? Well, I believe when you go to a lab, there's a thing called an amplifier, and that's the thermal amplifier.
Phase insensitive amplifier.
Yeah, what's that? There's a so classical source, ASC source, like amplified noise source. You generate those with these amplifiers. So classical, even classical communications, you have these amplifiers. So for example, when you do homodyne or heterodyne, if you have a classical coherent state, sometimes you amplify and then detect. So that's an amplifier. Entangled, okay.
Oh, sorry. Yeah.
Given noise channel, how the type of the state to use is typically chosen to give the best performance and the less vulnerability to noise. Yeah, let's say, depends on the task. Let's say you are doing classical communication, then you want to have the highest rate. Then the problem is how to design the encoding, whatever state you use to send 0 1 bits, and the maximum is the capacity. And then how to achieve that, you need the encodings. Oftentimes it might require complicated encodings of that are entangled in multiple channel uses. But for thermal loss channel or these Gaussian bosonic channels, one mode Gaussian bosonic channels we are considering here, actually, if you want to achieve the classical capacity, you just need to use coherent state Gaussian distributed to achieve it. But for other channels, like if you have phase noise, for pure dephasing noise, then you would guess number state is optimal to encode the classical message, which is the right intuition, because number state, if I send a single photon or 2 photon on the phase rotation, it's still a single photon or 2 photon. But for general non-Gaussian, let's say phase noise and the thermal loss channel, how to achieve the capacity, I believe it's an open question. People have different ways of achieving certain rate, I believe even the capacity is unknown. So lots of things to explore. And also for quantum capacity, then there's also similar problems, how to achieve the optimal, even sometimes what's the quantum capacity, it's unknown. So even the thermal loss channel, we don't know the exact quantum capacity. We know upper bound, we know lower bound, we know some good encoding. We even know some encoding that are better than just the single mode encoding. That's shown by Liang Jiang and Qin very recently. So simple channel that happens every day, thermal loss channel, even the quantum capacity, we don't know exactly what's the value. All right. So if there's no more questions, I think we can conclude. I will probably stay here for another 5 minutes in case somebody came up with any other question. But thanks for attending the course.
Yeah. Yeah, I'll hang out for a minute just in case.
Thank you, Quntao and Anthony. I'm going to put a link to the exit survey in the chat. And then when our attendees do close out of the Zoom, you'll also be taken to the survey page. We'll be following up with the recordings here in a couple weeks after we go through some editing. But otherwise, thank you all for attending. And Anthony, Quntao, thank you for taking the time to put the course together.
Oh, yeah. Our pleasure.
What type of physical systems can impose phase noise? Well, let's say you have a fiber link and you are sending states through the fiber link. If you know the fiber length, then it induces a phase factor like L divided by lambda times 2 pi. But if the path length is fluctuating, then the phase is fluctuating, then this causes phase noise.
Yeah, a similar thing with frequency fluctuation. Laser amplifiers, thermal input.
Yeah, thanks, Mike, for adding details. Standard laser amplifier is therma, in that if there's no input, the emitted light is thermal.
Phase noise, that's that. Thanks. Thank you, Anonymous. Okay. On the crossbar switch.
Can you discuss research on quantum crossbar switch? I don't exactly know what quantum crossbar switch is.
I don't either.
Are we assuming the quantum capacity of the thermal loss channel is achievable with a single photon encoding? No, that's probably not true. So the quantum capacity, which is the capacity of transmitting quantum information, that probably requires some challenging encoding. Yeah. So when you evaluate the capacity, it's a thermal state, but the actual encoding is actually more involved than that. I don't know that on top of my head, but I know that the GKP stays pretty well in achieving close to the optimums. Let's say if you send a single qubit through a mode, you can use these GKP states, Gaussian-Kilian-Presque states, to encode this qubit. And Liang Jiang, Qin and others, Victor Albert and others, Albert Victor and others, they show that it gets close to some bounds we know. And yeah, so what exactly should be better? It's an open question.
Yeah. Yeah, because like Quntao said before, we don't actually know what the quantum capacity is to begin with. But okay. Quantum dot computing.
Mike Raymer, 100 and 0 beam splitter is a cross-bus switch. In that case, it's trivial. The most just interchange. Yeah, thanks, Mike, for clarifying.
Mode swapper. Yeah.
Yeah, like a swap.
Yeah. Thanks, Mike. Thanks, Jerry.
Okay, I think it's probably time to close. All right, so did I just stop share and end the meeting, Brianna, or?
Yes, I'll go ahead and end the webinar now. Thank you all for joining us.
All right.
Yeah, thank you.